All right. Hello, everyone. Welcome to, well, I changed the workshop name a little bit, but this is essentially the machine learning / deep learning workshop. I did this workshop last year when I was an RTA, but I decided to change it a little bit so that it could focus more on deep learning rather than machine learning. So the last year's workshop is also on my YouTube channel. So if you want to go take a look at last year's workshop to get a more theoretical foundation than what I'll be showing today, then feel free to do that. But yeah, unfortunately, machine learning and deep learning is a very complicated topic. I only have 30 minutes to show you guys the coolest parts. So feel free, please, throughout the entire workshop, throw questions in the chat. I will leave enough time at the end to answer any of the questions they have, explore whatever you want. And yeah, without further ado, I'll just jump right into it. So you may be wondering, who exactly is Benson? Who am I? Well, I am a rising third-year computer science major at UCLA. I think my coolest credential was that I am a former GSET scholar. I went to GSET in 2020. I was also an RTA on the staff last year. So I love GSET, really fun, really awesome. Love seeing all of the scholars. Currently, I'm a software engineering intern at CrowdStrike. That's one of the top cybersecurity companies, really cool company. I also am one of the co-presidents for ACM Cyber at UCLA, which is the largest cybersecurity club at UCLA. I also do a little bit of undergraduate research involving security and privacy. So as you kind of see, I think cybersecurity is really cool. This is a little bit different because I traditionally don't spend a lot of time on AI, but I find AI to be a pretty cool topic. Hopefully I can share with you guys and get you excited with some of the fundamentals behind it. One thing I want to say thank you to everyone for filling out the Google form I sent out. Really appreciate hearing what you guys are interested in learning about. I went through some of the responses, and some of the very interesting responses I saw people wanted to learn about CNNs. A lot of people said deep learning. Some people said AI in medicine. Some said generative AI. And the reason I wanted to focus on deep learning is because AI is very complicated. It's a wide field. You could delve into natural language processing, computer vision, wide variety of topics. But fundamentally, the topic that's been causing the most research, the most development in AI that's caused the most breakthroughs is deep learning. Deep learning has allowed us to do things from creating cool artistic images generated by AI from things like you've heard of, such as maybe things like ChatGPT or DALL-E, those sort of models you've seen going viral, and also allows us to solve some of these problems, such as how we can apply AI in medicine. Maybe we could try to do cancer detection, or how we can handle image classification, recognizing different objects. All of these sort of tasks are possible due to deep learning. I will say I will not have time to answer or address all the topics, but what I'll do is I'll spend a little time after the workshop today to go through the document and or go through the responses to the forum and try to compile a document where I could link a bunch of stuff for you guys to check out, and I'll also forward that to the RTA. So if you have any questions after the workshop, please leave them on the Google form. I'll try to look at them and compile docs so I can try to answer whatever you want. But also please type in the chat. I'll try to answer questions throughout the workshop and definitely leave enough time at the end to explore some things if we have some time. But yeah, let's jump right into it. What exactly is machine learning and artificial intelligence? So there's this pretty cool definition by Alan Turing. If you don't know who Alan Turing is, he's considered a modern father of computer science, really cool guy. And so AI, in his definition, is the science and engineering of making intelligent machines. So you're teaching computers to sort of think by themselves. And within the field of AI, there's a lot of different parts. There's symbolic AI, stochastic AI, natural language processing, computer vision, a lot of different fields. But machine learning is one subset of that field, which we'll sort of focus on today. And within machine learning, there's an even more specific field called deep learning. And what machine learning is about, it's about taking data and you're sort of doing reverse programming. So if you see in this diagram over here on the bottom right, in a traditional computer and sort of programming scenario, right? Maybe you write a little Python program or something like that before. What you feed into your computer is you feed in your inputs to your program, your data, And you also feed in the program that you write yourself to your computer, and then it generates some sort of fixed outputs. But with machine learning, you're sort of doing the reverse of that. You're taking the data and the outputs that you already have, you feed it into the computer, and this generates the program for you. And there are a lot of techniques to sort of devise this sort of solution to come up with how exactly we can do machine learning. There's the main thing we'll focus on today is supervised learning, which is the most classical example of how to apply machine learning, where you have data with what are known as labels. Let's say you have an image of a cat. You label that with, okay, this is an image of a cat. But in some contexts, you also can apply unsupervised learning, where you don't apply labels. You just simply have unlabeled data, and the model figures out the labels by segmenting the different classes into different parts. And there's also this other really cool topic that I saw some of you mention that you're interested in. Reinforcement learning is quite cool. It's sort of this idea, if it, instead of taking a model, you have an intelligent agent, and you provide weights and biases to certain actions they can sort of do to give rewards, and so it goes from there to sort of figure out what is the best thing that sort of maximizes its reward. Those are all really cool. Oftentimes in machine learning and AI, you see combinations of these techniques. One famous example you guys probably heard about recently is, well, ChatGPT. ChatGPT incorporates both deep learning and reinforcement learning, pretty crazy. And it takes a sequence model known as GPT-3 and applies reinforcement learning on top of that, so that you can have the sort of chat experience that sort of have this sort of like memory it has within a given chat. So yeah, pretty cool stuff. So I'm going to sort of build up some of the basics of machine learning, and then we'll delve specifically into deep learning. So we're going to use linear regression as an example. So maybe many of you have taken a statistics class, or maybe your algebra class sort of covered this sort of topic. But when you're trying to do linear regression, right, you have a bunch of data points and you want to sort of find the line of best fit. Well, this line of best fit you can call, or a potential line of best fit, you call this your hypothesis function. And it's given by this equation over here, which you can have your hypothesis function have a couple of variables. Let's call them x and h of x. And these, your hypothesis function has parameters, which are things like the bias and the weight. The weight multiplies the variable. And these sort of parts all make up the hypothesis function. In machine learning, we call this a model. And the sort of goal is that we want to generate the best parameters, or the best weight and bias, the best values of this, so that it's best fits the data. So how do we determine what, how something best fits the data? Well, if you've taken a statistics class, we use something known as a loss function. So in traditional linear regression, we use mean square error, where we take the square of the difference between the expected and actual value. So the value on the line minus the actual data point based on the x value. And the sort of equation, or so the sort of hypothesis function that minimizes this error is the best model. It's the best hypothesis function. It's the optimized solution. And so why does this sort of relate to machine learning? Well, this sort of idea is the basis of machine learning. With statistical machine learning, you want to always find the best model. You want to optimize the parameters for the given variables or features that you sort of give input, and sort of go from there. But where the interesting part of machine learning comes in is that you as the programmer are not in control of the parameters, right? The computer is responsible for finding what the best parameters are. And so the only thing you can control are things called hyperparameters. So what exactly are hyperparameters? Well, these are things which affect the environment for learning. So maybe you want to use a different loss function from mean square error. There is something known as the Manhattan distance that you could use instead, which is like the absolute value rather than the mean square error. And changing these sort of different hyperparameters causes you to find the parameters, or the best sort of value of your function, your model, in a different way. Some things help you converge upon the best model a bit faster, which is part of the sort of engineering design of it. We want to converge upon the best model as fast as possible and improve learning as quickly as possible. And so how exactly do we do that? Well, one technique we sort of employ is a gradient descent. So a gradient descent, it's an algorithm for optimizing the loss function. So if you ever try to draw a line of best fit in your algebra class, you probably remember, well, how'd you sort of do it? Well, maybe you just eyeballed the dots on the plane and you just drew a line, or maybe you're like, okay, well, sort of fits the data points this way, but if I change the value this way, it changes to better fit, and you just sort of eyeball it. Well, with computer science and programming, we want to be more exact. We want to be have a more definitive algorithm to sort of figure this out. And so what we do is we sort of employ gradient descent, where the gradient, if you've taken calculus class before, the gradient is just a higher order derivative. And what is the derivative? Well, the derivative is just the slope of a function at a given point in time. So as you can see over here with the given multivariable sort of loss function we have over here, at some point we have where we want, we take the gradient at a certain point. So let's say right here, we multiply it by some value, which we call our learning rate. I'll talk a little bit more of that in a minute. And we try to work our way down. So why is it called gradient descent? Well, the gradient is the point of greatest ascent, right? Anytime you take the derivative point, it's the point of greatest ascent. So taking the negative of that value allows you to adjust the weights so that you go downwards, where you're minimizing the loss at a given point, and you adjust the weights this way. You adjust the weights so that each sort of weight is then optimized to minimize the loss function overall. And so I'll go a bit more in depth with this visualization right over here. So this is a cool visualization. I recommend checking it out. This is made by some people at my club at UCLA. And so as you can sort of see here, let's take a very simple loss function. Let's call it x squared. And we want to start at point 4 over here. What we could do is we could then, let's say by a given learning rate, at each point we take the derivative, we then apply this, we multiply the negative of this derivative by a learning rate, which is the value we set over here. And eventually this will converge towards the absolute minimum. Now, you may be wondering a few things. First of all, y equals x squared, right? You might be like, Benson, well, that's such a simple equation. I know how to solve this pretty easily. The optimized form is right here at the bottom. Why do I need to sort of go through this iterative process trying to figure out what exactly the minimum is, when I could just find the closed form solution of the optimized value right there? Well, oftentimes you will find loss landscapes or the sort of graphs generated by these loss functions. Well, they're not something that has a closed form solution. Oftentimes they look very ugly like this. They have local maxima, local minima within it, and you want to find the best absolute minimum, or sometimes they may not even have an absolute minimum. And so with these sort of equations, then it's sort of hard to figure out, well, what's the best solution? So this is why we apply gradient descent. Gradient descent allows us to minimize the loss, no matter whether or not the loss landscape has a closed form solution for the absolute minimum. And it allows us to figure out what is the best in the current context, the current initialization for a model, what we can sort of figure out from there. Pretty cool. Another thing you want to consider is that all of hyperparameters deal with learning and minimizing the loss function in some way. For example, another hyperparameter besides the loss function itself, actually, there are a few hyperparameters here. One, as of course, is the loss function itself, which we sort of define up here. Another is what we call the initialization, or the starting point. This can also be a hyperparameter as well. But the learning rate also matters quite a bit when determining your optimized speed for learning. And so, right now we have the learning rate set pretty low. We have it set to 0.25. But let's say we wanted to increase to maybe 0.75. What sort of happens here? Why do we want, why don't we just maximize the learning rate as big as possible? Well, what happens is we get sort of a zigzagging behavior. And in some cases, it does converge on the absolute minimum in some ways. But if you go a little bit too far with your learning rate, well, it may overshoot your minimum entirely. Or in this case, it doesn't even converge upon a minimum. But if we go a little bit higher, as you can sort of see, eventually it just goes off and it's nowhere close to near your absolute minimum. So your learning is really bad in this case. So you want to sort of figure out what is the optimized learning rate for your given your given function in your learning scenario. But with that, we're going to be jumping quite a bit fast. We're going to talk then a little bit about neural networks and deep learning. So deep learning is a subset of machine learning that focuses on neural networks specifically. What exactly are neural networks? Well, these are particular kinds of machine learning models that are modeled after the human brain. If you look into some of the nuances, the brain doesn't actually exactly work like this, but as a high-level inspiration abstraction for the sort of concept of neural networks, this is how this sort of process this original scientist sort of came to sort of this current idea. And so what is the idea behind neurons? Well, you have a bunch of layers, layers of your neural network, and each of these layers are composed of many artificial neurons. Each of these artificial neurons perform a form of regression called logistic regression. What this does is that it does the exact same thing as logistic regression, where you have to find a weight and a bias. Maybe this is a multivariable equation inside, and then you apply something on the outside called an activation function. What the goal of the activation function is that it often tries to take your your input from a continuous sort of domain to a discrete sort of domain. So what does that mean? Well, continuous means that you have things like decimals. Maybe your output of your regression is 0.52, and you only want it to be integer values, discrete values. So you use an activation function to take it from the continuous sort of domain to the discrete sort of domain. This is important because this allows us to solve a different problem in machine learning and artificial intelligence. The first problem I showed you is known as regression, where you're trying to take a numeric input and map it to a numeric output. But what classification does is that it takes a discrete, sometimes numeric input, and it takes this input and produces a discrete output. So one example is image classification, where you want to take an image and you want to then say, well, is this a dog? Is this a cat? Is this a bear? Things like that. Those are classes. Those are discrete outputs where there's only a finite number of outputs. And a little more terminology. These neural networks, these artificial neurons, then when combined together, these form perceptrons. And these perceptrons then compose of multiple layers. So if you see in this bottom right-hand corner over here, this is a single layer neural network. The reason why despite you seeing possibly three things that it's considered a single layer neural network, is we count the hidden layers. So what are hidden layers? Well, they are the layers in the middle. You have your input layer, your output layer, and your hidden layers. And so there could be multiple hidden layers. Oftentimes, some models get very complicated. There are hundreds, if not hundreds of thousands of hidden layers in the model, adding to its complexity. And the sort of idea is that by having more layers, you increase the possible complexity of the overall model that you have, the overall function that you can sort of map in this sort of domain. And oftentimes, right, you're not dealing with things that only have two variables or two features. You're dealing with things that have 3, 4, 8, hundreds of thousands, if not millions of features in some very complicated models, such as maybe ChatGPT and things like that. Those models take in larger amounts of input, and because of that, they're able to do more complicated things because there are more sophisticated models. To sort of visualize a little bit on how, if I could exit my full screen for a second, to sort of visualize what exactly this sort of looks like, if you go to this website, I recommend checking this out. This was implemented by TensorFlow. TensorFlow is one of the libraries used in machine learning that's quite popular in industry. You can sort of see what's sort of going on over here. Well, you have another one-layer neural network, but which maps two features to which go eventually to, oh, sorry, there are two hidden layers. I missed this layer over here. And this goes to one output, which is to determine the overall model over here. And you can see things involving the hyperparameters surrounding this, right? You have your learning rates, which we talked a little bit about, activation function. You can apply something known as regularization, if you like. And this solves the classification problem, which determining in this sort of data set, what's the difference between these blue and orange dots. And so if we run this, we could train this for multiple epochs. Each epoch is one time through the overall training data. Every time we go through this, well, we could form the overall model. And as you see over here, the overall loss from our loss function, well, it's actually pretty good. It's quite low. We are converging on a model that has a pretty high accuracy. But with that, oftentimes, I think with a lot of these workshops, we talk a lot about theory. We don't get to see it in practice. So I wanted to do a quick demonstration, which this machine learning library called PyTorch. PyTorch, if you are interested in deep learning and especially machine learning research, you definitely want to learn PyTorch. This is used in academia most often, but oftentimes this is also used in industry as well. PyTorch was invented by Facebook, so some companies use it to do very complicated things such as self-driving cars or email filtering. A lot of industry applications use PyTorch as well, so it's a great machine learning library to learn. I will just briefly go through the sort of code here, because if I were to run this code, I ran this a little bit before the workshop, but if I were to run this code, this would probably take like 20 minutes to run. So I definitely try to highlight the parts that you could run this yourself. I'll send this link out as well with the slides a bit later. But the first thing you're sort of wondering, what exactly am I on here? Well, this is an application known as Google Colab. You could access this directly in Google Drive. What is Google Colab? Well, this is an interactive notebook. It allows you to run Python code in these particular cells. Each cell runs its code separately from each other. And so you could do things like run certain cells multiple times, which is pretty useful, and also get visualizations. You can add your own text with Markdown, and you could get save outputs and so forth, as you see later on. But let's sort of go through the code sort of here. We import PyTorch, which you can just do by import torch. Torch Vision is a supporting library for PyTorch. It allows you, it provides things such as data sets and sort of other things such as transformations, which help you do things called data augmentation, or create more data from your underlying data. And so there are also some supporting libraries I had here. TQDM is just something that shows you what progress you sort of made, and Matplotlib helps you visualize graphs and things like that. But the first thing you want to do whenever you go into Google Colab is you want to go to this runtime tab, and you want to click change the runtime type. And so machine learning is a very interdisciplinary sort of subject matter. You have both the software side of things and also the hardware side of things interacting together to sort of help build an overall better learning situation for machine learning engineers. And so you want to incorporate this sort of tab over here. Before, I think by default it's selected by none, but since I ran it before, I have the GPU turned on. What exactly is a GPU? Well, a GPU is a particular type of computer chip which has optimized hardware for math and matrix multiplication. Particularly, this is useful for machine learning because this allows you to do your machine learning a lot faster. And so Google Colab allows you to access some GPUs for free. So if you want to accelerate your machine learning, instead of waiting on your local computer's CPU, which would take much, much longer, using a GPU definitely helps accelerate your learning. You want to click save and go from there. Then you want to move PyTorch to your GPU for usage. So the GPU used here uses this software library known as CUDA, which is developed by this company NVIDIA. NVIDIA is the dominant sort of company in the sort of hardware acceleration for AI. That's why they're making billions and trillions of dollars. So they're a pretty cool company. Definitely should check them out. But what we do here is that we move PyTorch over to the GPU so that it knows that, well, I can sort of use and do all of my fancy math on this particular hardware instead of my normal CPU. Then we set up transforms, which allows us to take our data and convert it to tensors. Tensors are just higher order matrices. So if you've taken linear algebra before, a matrix is just sort of like a two-dimensional array of numbers. Well, a tensor is sort of a higher dimensional matrix where you have like three-dimensional, fourth-dimensional, eighth-dimensional matrices. And this is what's used to sort of apply and do the fancy tensor math behind machine learning. Then you take your data. And so you see I have two types of data sets here. I have training data and testing data. The difference between the two is that, well, training data is used to actually do the training, while testing data just simply applies validation on the overall training. Then I load the data. And so the particular data we're working with here is known as SciFar 10. 10 because they are 10 images. There are 10 different kinds of images, each focusing on a different kind of class. And there are a lot of images in this data set. And what we do then is we define our neural networks architecture. I called it GSET, pretty funny, and apply a different bunch of layers. And then we define a function called forward. Forward is what's called when you want to do your machine learning. We then define our model by changing it to the GPU. And this is where we define our criterion as well. Our criterion is our loss function. This is the thing where we determine, well, how well is our model learning? And we also define something called an optimizer. An optimizer is one of the few things that helps improve our gradient descent. So Atom is a very popular optimizer. There's a lot of research being done on improving optimizers. And we define our learning rate over here and also something called weight decay. We then define this sort of supplemental function over here, which helps us determine the accuracy of the model, as in how many times are we predicting the right thing throughout the training process. And this is what takes the bulk of the time over here. This is the actual machine learning training. I just define a quick progress bar, and then I train it for 6,400 iterations. The difference between another term you might often hear is an epoch. An epoch means that you go through the training data one time. So you go through all the examples one time, performing gradient descent, and also something called backwards propagation, which is sort of defined over here. Iteration, what it does is that it, instead of doing it per epoch, it does it per batch size. And what batch size is sort of defined over here. This is the number of examples in a batch. And the reason why you do this is that this provides a higher level of granularity for your training. And so you do this, I log this accuracies at every 100 sort of parts of the training. It takes the inputs and labels, it puts them on the GPU, it runs it through the model, and then it calculates the resulting loss function from that, and then performs backwards propagation, which allows it to calculate the gradients for gradient descent and sort of figure out, well, how can I then know where to go and optimize the weights from there. Then I save the model so that I can use it for later. Obviously, when you run a model, you don't want to just run it one time, you want to run it multiple times. So that I load the model, I evaluate it, and then I could try to determine how accurate my model is overall. As you can see, I did an okay job. I did 83% accuracy for this particular model. And you can sort of see the output sort of over here in the end, where I just randomly pick an image from the testing data set. I picked airplane, the model then properly predicted it's an airplane. So that's pretty cool. This is a neural network that solves this problem of image classification pretty quickly. I am going to continue to speed through some of these parts over here. I'm a bit biased since I come from a security background, so I want to talk about something that's pretty cool involving AI security. This is a problem known as adversarial examples. So particularly if you want to learn about hacking AI, this is particularly cool. And so the problem we sort of have here is that the model originally predicts an image is sort of by this label. This image is of a panda according to the model. And what we're trying to do is that we're trying to change the image so slightly that, well, to a human eye, it doesn't look to change it at all. But to the machine learning model, it thinks it's something completely different. This is a very important problem because this is an unsolved problem in machine learning. There's over 2,000 research papers on this sort of problem, and well, there's no solution. A lot of very smart people have worked on this. Why is this important? Well, you can see over here in this bottom example, let's say the model tries to do something for self-driving cars. You then have tape on a stop sign for trying to determine whether or not a car should stop. And if the tape is provides an adversarial example for the self-driving car, then the model is able to maybe the model then misses the stop sign and then causes an accident, which would be terrible. The sort of analogy to the human brain you can sort of think about is you then sort of think about optical illusions, right? Optical illusions often, are things that look normal, but they trick the human brain. And that's the sort of analogy with neural networks. A particular kind of attack is known as the fast gradient sign method. I'm going to skip through this slide since I'm a little low on time. But if you want to try this attack for yourself, this takes advantage of gradient descent and performs an attack via gradient ascent. There's a notebook over here if you want to try running the attack yourself. It's pretty cool. Definitely recommend checking it out. There are a lot of different AI threat models with artificial intelligence. There's poisoning, sort of more adversarial examples. You can even extract models and figure out training data from that. AI is becoming something that requires not only people from the engineering side, but also from the security side to be concerned as well, because, well, you may have people attacking very important models such as self-driving cars, or maybe large language models like ChatGPT, which is also pretty important as well. But with that being said, I see I did get 5 additional minutes. That's perfectly okay. I saw you guys had a lot of questions, so I'm curious if you want to put any questions in the chat, or if you want me to go back, explain something, because I just lightning ran through this entire presentation. Yeah, I'm curious if you guys have any questions. I'd be happy to answer them. I also recommend looking at these sort of links I sort of provided over here. I ran a workshop last year where I go into a bit more of the theory. Definitely recommend checking that out. If you want to get really good at deep learning, this is the book you should probably read. You should definitely read this book. This is written by Ian Goodfellow. He is one of the inventors of GANs, if you've heard of that before. He's really smart. You should definitely read his book. If you want to learn more about PyTorch, here's a cool video to learn that. And also, if you want to hear more about adversarial examples and AI security, you should watch this video. This is a 2-hour workshop I put together with my friend about the topic, so definitely watch that. A quick shout out as well. I want to say thank you to my good friend Jordan Lin. He's the president of ACM AI, the AI club at UCLA, and he helped me develop some of this content. He's also really good at AI, so I want to quickly thank him for that. But yeah, I'll answer some of these questions. Great first question. How would you get started with machine/deep learning? I'm a big fan of just trying things. So maybe I'll send a link to the notebook. Try running the notebook, figuring out how to maybe generate a high accuracy model from there. Getting familiar with PyTorch, getting hands-on, I think, is what's recommended. I then recommend maybe when you're in college, or Andrew Ng from Stanford University has a lot of great courses online. Definitely recommend checking that as well. Max also recommends a great website. Kaggle is also really cool. There's a lot of good resources on there. What are the most common applications of transfer learning? So transfer learning is really cool. Basically, the biggest bottleneck with a lot of machine learning models is that you need a lot of data but oftentimes with some problems, you just simply don't have enough data. So what you could do is you could train a model on a similar problem, like you train a CIFAR-10 model on this data set for classification, and then you could then fine tune the model that you get from this sort of CIFAR-10 training and apply it to a different problem. Let's say you want to classify just cats and dogs. And what transfer learning has done, there's been empirical and mathematical evidence sort of showing that this improves the accuracy of the model, just not starting from scratch by applying a different initialization from a different problem. Another great question. How much Python experience should you have before starting to learn machine learning? Just start. I think you can learn Python as you go. Machine learning has a lot of abstraction, so there's a lot of high-level stuff. I think definitely some of the syntax of machine learning is definitely library specific, so don't be afraid to just get started. I'm a big fan of just getting through that. All right, let's see. I see some questions about FGSM and adversarial examples. I'll come back to that since there's a lot of other questions. I definitely recommend watching if you have the time, watching the 2-hour workshop I shared the recording of. There's a lot of experience. There's a lot of time. We put a lot of time into explaining some of the concepts in there. Are 10 images per object enough for the CNN or the data augmentation shared a lot of training? Oh, sorry, I misspoke. So there are not 10 images for each class for CIFAR-10. There are 10 classes in CIFAR-10. So there's like cat, airplane, horse, things like that in CIFAR-10. And each class has like several thousand images within it to represent each sort of class. But you also apply data augmentation of it by doing things like take an image, maybe you want to flip the image to create a new example with the image flipped, maybe turn it upside down, maybe add a little bit of noise, things like that. Those are things that you can sort of do to sort of create more data. Do I think AI could ever or would ever become sentient? No comment on that. I will say some very smart people at Google and Facebook have said that they already think that they have a sentient AI model there, but I don't really have a comment on whether or not that's true. Reinforcement learning. So reinforcement learning is quite cool as well. It is very different from supervised learning in that for supervised learning, the sort of hyperparameters we set involve determining whether or not the loss function and determining whether or not things are sort of gone in that sort of direction. With reinforcement learning, you're trying to set hyperparameters involving things like, let's say you want maybe like an intelligent agent to play a game. Well, maybe you add sort of extra points to certain rewards for the agent to maybe like, okay, walk forward, maybe jump over a wall, collect this coin, things like that. Those are things with reinforcement learning where you apply sort of hyperparameters for what are things that will give the agent reward, and also you apply things that would provide a penalty to the agent to sort of so that it tries to maximize its reward, and sort of goes from there to sort of figure out what's the sort of best scenario for that sort of reinforcement learning case. What types of learning is used in applications like ZeroGPT and other AI detection software? I actually saw this question on the Google forum. And so this question is actually very interesting because there's actually a research paper that came out a little while ago that empirically and theoretically proved that if you are unable to discern AI generated text from like human text, like any sort of application sort of contesting that it's able to sort of discern or classify AI detected tests, AI generated text from human text. Well, that's according to this paper, that's simply not true. But there are techniques that companies and sort of developers sort of cheat to sort of figure out how to sort of detect AI text. So one technique is watermarking, where an AI that generates text slips in undetectable watermark or certain parts of the text that are untraceable to a human reading it, but a different model can determine, oh, well, it's generated by this AI because it left this watermark. And yeah, that's something, that's a pretty cool example. Another great, interesting question, can humans still differentiate AI text from human text? That is, well, hopefully the people developing the generative model don't like make it easy to determine the two. Ideally, you want to close the gap between human generated text and AI generated text so that that's the most optimized sort of scenario. There are a lot of questions. If you have additional questions, I'll send out the Google form to the Google Slides to the RTA. There's a Google form on there. Just fill out with additional questions, and I'll try to compile a doc which sort of answer them. I do want to end on one sort of very interesting idea. So one of my professors at UCLA who does a lot of AI research, he sort of talks about how exactly do we find the best hyperparameters, right? That's something that you guys may be wondering from being introduced that today. So because with finding parameters, there's a very clear definition. We have to minimize the loss function. With hyperparameters, the way we sort of find the best sort of solution is, well, we can't really determine mathematically. Sometimes we don't even actually know why certain hyperparameters are really good. The way we sort of do that is we just find it by experimentation. We find it empirically, and we sort of go from there. And I think this idea is actually quite cool because this sort of demonstrates true computer science, right? Anytime you perform or train an AI, you're not performing a programming task, you're performing a science experiment. You're trying to create this hypothesis that, well, this architecture, these sort of hyperparameters will improve the best accuracy for this sort of problem. And you sort of change the values as you go to determine from iterative experiments, how to sort of determine what's the best sort of scenario for learning. So I definitely recommend the best way to try to mess with this stuff is try hands-on. I'll send out the Google Colab notebook to sort of figure out where to go from there. And I know I'm 2 minutes over time, so I want to thank the RTA staff for letting me ramble a bit on answering the question. Please, if you have any questions, I'll be happy to answer them. Just put them on the Google form, and I'll try to compile docs so that any questions you have, you'll be able to read and look up some answers for a bit later so you can learn more about machine learning. But with that, thank you for having me here. I love being back at GSET. Thank you again to the RTA staff for having me. I hope I didn't go too over time so that you guys can still run to your next class. But yeah, thank you so much.